Thanks a lot for your kind invitation for me to present our research development. Today, I'm going to present a very similar topic that what Professor Tang Wu presented, but we have some experimental results that we want to share. It is mainly about real-time aero-elastic hybrid simulation method that we have developed for buildings as well as for bridges as well. So the work has been mainly done by graduate students that I'm supervising or co-supervising at the University of Toronto or Seoul National University. Let me see. Yeah. So the students from U of T were mainly focusing on the building model, and the students from Seoul National University were mainly focusing on the bridge section model, and we carried out experiment at the Gradient Wind Engineers in Ottawa, Canada. And for a bridge test, we carried out tests at Seoul National University. So today I'm going to give a little bit of background about hybrid simulation. It's a very high level background and a few examples in seismic applications. And then I'm going to present the overall framework for real-time aero-elastic hybrid simulation and share some experimental results. And I'm going to briefly summarize what we have developed so far. So as you all know, in the field of structural engineering, we still do a lot of experiments. And we do experiment because we cannot numerically model complex behavior of structural elements subject to extreme loads, such as wind or fire or seismic excitations. So various testing methods we use for various needs, including wind tunnel test, as I just briefly, as I showed you here as well. We have limitations in experimental studies, however. Because the scale of the structure is so large in civil engineering, we cannot test a building or bridge. Typically, you test a small scale building or only component level test. If we do run component level test, we cannot have bidirectional interaction between the component level test with the structural system. So it can be very well defined and small, rather a small scale test, not typically full scale component test either. And when you run wind tunnel test, there is also some limitations as well. There is some scaling issue, as well as the if we want to run aero-elastic test, we cannot properly model the influence of AMDs and TMDs or any other supplemental damping devices in the aero-elastic test. So somehow we greatly simplify the modes of vibration of the building model or bridge deck section model and run the test. So there are some limitations in the experimental studies. To overcome the limitations in both numerical and experimental studies, the concept of a hybrid simulation has been developed. It has been developed from 1960s from Japan for seismic applications. And the main idea of hybrid simulation, as Professor Tang Wu noted, it is to take advantage of the numerical model as well as to from the experimental test. So by modeling, numerical modeling that we can model confidently, by numerical modeling the areas of a building that we can model confidently, is represented as a numerical model. And for the elements that cannot be modeled numerically, is modeled physically. And then we combine both of them to represent the system model. That is the main idea of hybrid simulation method. If I give you just some brief background a little bit further, this is the equation of motion that we solve typically. It doesn't matter whether this equation of motion is for wind engineering or for seismic engineering. We are solving this equation of motion for the case of seismic engineering or earthquake engineering. The component that is hard to model numerically is typically the restoring force. So we formulate this restoring force vector partially from a numerical model, if we can do it accurately, and partially from experimental specimen. And then we combine them and we run simulation. That is the concept of hybrid simulation. For the case of seismic or earthquake engineering, we have pretty good precision in terms of modeling the inertial force or inherent damping or the applied force. So we are pretty confident about that, but this part is difficult. That's why we run hybrid simulation, modeling this restoring force experimentally. Just give you one example. This is a 4-story braced building where there are yielding, cast steel yielding components at the end of the brace. we can, because this yielding braces hysteretic behavior is rather complicated, we can put these elements in the lab and combine these brace elements with the numerical model in OpenSys and run hybrid simulation to understand how these brace behavior or yielding elements behavior influence over the overall response of the building. We can do similar approach for the case of fire engineering as well. We are solving exactly the same problem, except that the rate-dependent terms disappears and the restoring force is a function of deformation as well as temperature. And if we assume that the rest of the building is can be modeled numerically, we can model only the critical elements subject to fire because it is difficult to numerically model this element, which is subject to very high temperature and high load. So in this situation, we can model this part experimentally and part the rest numerically and connect them and run simulation to understand how this element interact with the rest of the system as we apply gravity load and as we heat the specimen and as well as in the cooling phase. So at the end of the test, we can tell how much plastic deformation is developed in the system when there is interaction between a numerical model and a physical specimen subjected to fire load. In fact, the wind engineering is a quite similar problem. There has been some studies about application of hybrid simulation in wind engineering, especially in real-time aero-elastic hybrid simulation. As previous presenter noted, Kanda et al. Is someone that we can find as the early study, developed hybrid simulation method for building, where they used the load cells in the beginning and later on in 2014, they used the pressure taps to evaluate force from wind as a pressure from pressure sensors. Professor Wu's group did some feasibility study about aero-elastic hybrid simulation of a bridge deck. In 2019, our group also developed a design of the experimental setup, and at that time we submitted a conference paper because we were working on experiment at the time. So today's presentation is mainly about the development of experimental setup and test results for aero-elastic hybrid simulation. So as an advantage of running real-time aero-elastic hybrid simulation, there are various advantages. So first of all, unlike the experimental using spring and mass for conventional aero-elastic hybrid test, we can define stiffness, damping, or model parameters quite easily using a numerical model. So you can just define mass metrics or damping metrics in the control system. And I think it would be possible to model more than 2 modes of vibration for the bridge deck simulation. And also, we can model supplemental damping numerically. For example, if you run aero-elastic test of a building, if needed, we can put nonlinear damping or TMD or AMD in a control system, while the wind structure interaction can be represented experimentally. And also we think that real-time aero-elastic hybrid simulation will also improve our understanding of wind structure interaction because we can measure wind force and structural vibration and the influence of damping on wind structure interaction as well. So without further ado, I am going to go over more details about our development. This is the same equation that I showed you, except that the right-hand side is the wind-induced force. So if we have a structure, either bridge or a building, we are solving this equation. Unlike a structure that is subject to seismic load, a structure subject to wind load behaves mostly in the elastic range. So we can confidently model the left-hand side of the equation. However, the right-hand side of the equation is a wind-induced force, which is a function of the deformation of the specimen. So like this angles and velocity of the deck or the of the building. So we cannot predefine the right-hand side of the equation, and that's why we need to run aero-elastic tests to understand how this wind-induced force influence the response and how the structural response influence the wind-induced force as well. So because we have confidence that we can model this part numerically, we just put it in the numerical model and obtain this external force due to considering wind structure interaction experimentally and feed it back to the equation of motion. That is the steps that we solve. There is one challenge though. When we take this approach, we use load cell to measure wind-induced force, but we cannot make a specimen without any mass. Whatever material we use, the specimen should have some mass. So some of the inertial force term in the equation is measured through the load cell in the system. We cannot just remove it from the load cell. We are developing several strategies to compensate this issue. And today I'm going to show you one of the methods that we are using. So now how the overall control system works. We need to solve the equation of motion. So this part is the numerical integration scheme. There we solve the equation of motion. And because there is some delay and tracking error in the actuator, we need to have a delay compensation scheme. And the motor control that we are using doesn't have much role. It just transmits data from the delay compensation scheme to the motor driver. And then motor driver runs PID control loop to control the linear motor, and linear motor control the motion of the specimen. I'm just giving an example as a building model, but the bridge deck section model is exactly the same. And the measured force, which is calculated, obtained from the load cell, is fed back to the numerical integration scheme. And we repeat this process several hundred times per second. In terms of the numerical integration scheme, we are using central difference method. But as I mentioned before, if this is the central difference equation of motion for this system, some of the inertial force components, let's call numerical mass and experimental mass. So this experimental mass inertial force component is on the right-hand side because this is measured from the load cell. So equation of motion needs to be slightly modified to accommodate some of the inertial force that is measured from the load cell. So equation of motion is now modified in this way. Once we convert this one to a discrete equation of motion, different equation of motion, then we are solving this problem now. So at each time step, we predict the motion or position of the actuator or position of the rotation angle, which will be later translated back to the actuator's movement using the central difference method. That becomes target deformation. But there is delay in the experimental setup always. There is the actuator delay due to various issues like mostly in the actuator's response, and the other term factors are rather minor. So when we solve this equation, the measured force, in fact, is not corresponding to the target displacement that we are given. At theta I, once we issue command, actuator need to move. So at least there's a one-step delay between the command and measurement, and there is various other delays in the system. There is some substantial consequence of delay in real-time hybrid simulation. What happens is this. The vertical axis is the inertial force from the experimental specimen. The horizontal axis is the commanded displacement. Once we issue a command, because the actuator cannot follow the command, there is a little bit of delay, the measured inertial force is due to the acceleration at a few milliseconds before. So we are measuring force not at theta ti, but at theta t sub I minus delta t. Once we issue a new command, there's also another delay. So eventually this creates a loop, which is the additional damping effect. In real-time hybrid simulation of structure subject to earthquake load, when we model this term, which is the displacement proportional term, or displacement dependent term, the delay typically lead to negative damping and lead to a stability issue. In our approach in real-time hybrid simulation of structure subject to wind load, because the inertial force is measured, which is the second derivative of displacement, we have positive damping effect due to delay. So we mathematically derive how this delay influence the additional damping and what factors influence this additional damping. So we realize that the delay itself and natural frequency of the system and the mass ratio, mass between experimental mass and the total mass, the mass ratio influence the damping ratio. And then to compensate the delay, in our test that is carried out in 2019 with the building structure, we used the inverse delay compensation scheme by Chen in 2007. It worked up to a certain extent, but it was not most optimal method. So we improved the delay compensation scheme using adaptive inverse delay compensation scheme at the later stage. So I don't have that result. I have some result here, probably, but that the presentation is mainly from the experiment that was carried out using the inverse delay compensation scheme. And then motor driver controls the motion of the linear motor. This linear motor has precision of, if I remember correctly, 1 to 5 micron, 1 or 5, I don't remember correctly. So it has pretty high precision linear motor, and this linear motor's position is controlled using the motor driver, using various control loops internally. And before we run experiment, we tune the control parameters as much as we can, so we can have proper tracking of the position, and then we use the delay compensation loop to minimize the delay between the command and the signal. So in terms of hardware for building experimental setup, we have this building experimental setup and this numerical computation for numerical integration and delay compensation is carried out in the NI hardware in a compact deck. It has its own processor in it. And the motor controller, this yellow box, it just transmits data between the devices. It doesn't have much role in the hybrid simulation. The motor controller, this one runs PID loop. And then we have a linear motor in the system, etc. For bridge test, however, we are using different control schema. We were using EtherCAT controller without using this one, which was much faster as well, and we are improving some error compensation scheme as well. We are working on a paper from the experimental result of the bridge testing setup. In terms of hardware for building apparatus, we are developing base pivoting motion by using linear motor and installing loader cell at the linear motor, so you can read the inertial force as well as the wind-induced force. And we are also at the stage of improving this force measurement to have better precision. It was not a good idea to put it here. It should have been better put it somewhere up here. So we are changing the some of the designs as well. The design of the experimental setup was done such that, so you can see these link elements as well and the specimen mount. Design of the experimental setup was done such that we can have two DOF motion. Primarily, this across wind direction vibration is the main concern, but we also want to control the along wind direction as well. So after we completed the crosswind direction hybrid simulation, we are at the stage of assembling the 2 DOF experimental system. In terms of bridge deck section model, the conventional test is carried out using spring mass damper system. And as you can tell here, this damping device is highly inaccurate. If you evaluate the damping properties at different frequencies and different amplitude, it is highly random. If we want to have 0.5% of damping, it's really hard to achieve at certain level of amplitude and the frequency. So that's why we want to control the motion of the bridge deck section using four linear motors, where by moving the vertical motions independently, we can control the vertical motion as well as the torsional response of the bridge deck section model. We put bidirectional loader cells to measure the wind-induced force as well as the inertial force of the specimen. And we need to design several connections to allow development of mechanism between the two linear motors without developing friction as well. That is the experiment, how the experimental setup looks like once we attach to a wind tunnel in Seoul National University. So now I'm going to share a few experimental results. So before you run actual hybrid simulation, we need to test a lot of steps before you run it. So in this big picture that I showed you earlier, let us turn off numerical integration, turn off force feedback, and do not blow wind. We want to check how the imposed displacement command is executed by the linear motor, and we want to understand the delay and the phase error or the amplitude error when we use the inverse delay compensation scheme. We realize that when we do not use inverse delay compensation scheme, which is when alpha equals 0, the delay was about 29 milliseconds. As we increase the value of alpha, the delay was decreasing. However, there is quite significant magnitude error. So we ended up using alpha value of 3, and which was not optimal, but we could maintain a good magnitude error, but we still see 25 millisecond of delay, which was quite significant. But at the later stage, we implemented adaptive inverse delay compensation scheme, which led to around 1 to 2 millisecond of delay only. So this was a rather earlier results from earlier study. Okay, so now, and then what we do is this. We do not turn on wind, but we run numerical integration. By doing this, we can run free vibration tests. So if we impose a certain level of initial deformation or velocity, then the structure should vibrate and as if it has a spring and mass, and then it should go back to the original configuration. So we define several mass density of the building, and then the physical mass of the specimen itself is fixed because we don't want to change specimens every time. And we define the various input damping properties as well as input frequencies. For example, if I show you one of the case here, you can see that between the target command, the red line, and measured response, there's around 25 millisecond delay from the earlier study. Now it is much better. Because of this delay, there was some additional damping that is produced. So this test is the one without any wind, but with force feedback and with numerical integration. As you can see now, even though there is no spring and mass and damper, it is all just experimentally controlled. I can push, I can release, and it acts as if it has a spring, mass, and damper. Once we run the experiment, it results look like this. For example, when we impose when you define 6 hertz of specimen's natural frequency and specify damping ratio of 0%, so 6 hertz and 0%, what we observed from that free vibration test was 6 hertz, so the frequency is correct, but we observed 2.4% of damping, even though we specify 0. This 2.4% of damping error, additional damping, is due to the delay, mainly due to the delay. So we ran many of these tests, and we found that the equation that we derived is correct. So evaluated damping from experiment and the evaluated damping from the equation was quite consistent. And then we are having confidence regarding how the system works. The reason that we ran this many tests earlier is that because at that time you couldn't reduce the delay sufficiently, we want to have sort of calibration table. So if we want to have 2% of damping with a 6 hertz of vibration, then we need to import 0% of damping in the numerical model, for example. In certain cases, to achieve 1% of damping, you need to define negative damping in the numerical model, then it becomes 1%. Now the situation is a little bit different. We can control the damping much more accurately because the delay is smaller. And then what you do with the building setup is the real-time aeroelastic dynamic test. So we turn on wind, we turn on numerical integration as well, and then we run the system. We run the system with various numerical mass, so with various mass density of the building, and also we ran the conventional hybrid test with a conventional spring mass damper system. So for example, if we run the test, this is the way it is vibrating. So even though there is no spring mass and damper system, it was vibrating. As you can see, it was not deformation of the building, but base pivoting imposed by the motor. The conventional aeroelastic setup is a base pivoting model where deformation is measured using a laser transducer, and spring and mass were tuned such that the damping property and frequency is matched. But when you ran the experiment, we didn't realize that Scruton number has big influence in the response. So in fact, the Scruton number or mass damping parameter were inconsistent with the cases that we ran with the real-time aeroelastic hybrid simulation. So mass damping parameter was much less in the case of conventional aeroelastic test. So if we compare the experimental result, the real-time aeroelastic hybrid simulation that we carried out was R sub 1 and R sub 3, and the conventional test was this one, and the reduced velocity or wind speed where the vortex-induced vibration developed was quite similar, but the amplitude of vibration was different because R sub 1 and R sub 3 and conventional test had a different Scruton number. And with the Kato and Kanda case, the red one, the results are different because the aspect ratio was different as well as the Scruton number was different. Also, the types of wind was different as well. So that is why we have some discrepancy here. If we run the test again, probably we'll control the testing parameters more carefully so you can have a more comparable comparison. As you all know, in the first, this was in fact the first aeroelastic hybrid simulation, and we were having only 3 days to run the experiment. So that was all the test results that we could get. For the case of bridge test, we run something similar. As you can see, a student is imposing a load to a system. The system is deforming, and then once we release, it is vibrating. This level of deformation is perfectly same as the stiffness of the system that is defined numerically, and the damping ratio was quite similar. As you can see, this one, the damping is what is specified was 0.280%, and the expected damping ratio is 0.27 to 0.3%, and the actual damping ratio measured was 0.28%. So it was quite consistent. And then we ran aero-elastic hybrid simulation as well, and made a comparison with several different cases. So first one is the spring support. So for the exactly same specimen, they built a spring mass damper system. Spring mass damper system. Spring mass damper system and run experiment. And then we also ran the real-time aero-elastic hybrid simulation with a different Scruton number. And as you can see, the response with vortex-induced vibration is quite similar. The wind speed at that developed vortex-induced vibration is quite similar. And the vertical displacement is different because the Scruton numbers are different. For now, we are modeling only the vertical DOF. We need to couple the rotational DOF and vertical DOF. That is what we are currently working on right now. Okay, in short, we have developed the testing apparatus for aeroelastic hybrid simulation of base pivoting building model and a bridge deck section model. And in real-time aeroelastic hybrid simulation, the delay in the actual response leads to positive damping effect. So we need to compensate for it. And one of the methods is just tweaking the equation of motion such that the numerical mass is reduced a little bit, and that term goes to the right-hand side, which is measured. We are developing a new method to compensate the error more effectively as well. We have validated the developed experimental setup, experimental method in the wind tunnel test for both building and for the bridge as well. And I think once it is fully developed, it can expedite the prototyping of a building geometry. They can just build a model, assuming the building model itself is not too heavy, and then put it in the experimental setup and run experiment quite easily. Kanda's method in 2013 in earlier study was using pressure taps and then the integration of the pressure from pressure taps. But the reason that we are using loader cell is mainly one reason. In real buildings, there are many high-rise buildings with quite complex geometry, with some torsional geometry like that. And installing pressure taps and taking integration and getting force component only in the direction of across wind or along wind direction will be very difficult, and it takes a lot of time to fabricate such a model as well. So we are using load cells to measure wind-induced force. As a side effect, we are measuring inertial force. This is the negative side, but we are developing methods to compensate the measured inertial force from the equation of motion. With that, I'd like to conclude my presentation. And if you have any questions, I'm happy to answer any questions you have. Thank you.
Thank you very much, Dr. Kwan. Great presentation, very, very informative. 2 projects, so thank you very much. I see 2 questions from Professor Jim Rickles. Dr. Rickles, would you like to discuss that?
Yeah, Kwan, a very interesting presentation, but I have a couple of intriguing questions for you. One is you used the central difference scheme. What was the thinking behind that? Because it's only conditionally stable and very limited. And what I'm asking is, have you tried other methods. The other thing is being an explicit method. If you ever develop nonlinearities, you're going to run into trouble with spurious higher modes participating, which will make it unstable because of the need for controlled numerical damping. So have you tried other schemes besides the central difference method?
No, we haven't tried any different method, but in this simulation, we are using very small time step anyway, so we haven't seen any stability issue resulting from central difference method. And the system is behaving linear.
System's linear, right?
Yes, the system is linear.
Yeah, so I think you're going to run into problems when it goes nonlinear, because you're going to get change of state, which generates acceleration pulses, what's called the Nyquist frequency. So something to just think about. But in any event, it's good progress. But the other thing I wanted to ask you about, and it seemed counterintuitive based on other studies, is that damping creates, delay creates positive damping. I mean, studies have shown that it actually creates what the equivalent of negative damping. And what I mean by that is, as you increase the delay, if that were true, that it causes positive damping, eventually the structure would not move. But in reality, what happens is the poles migrate, especially in a state space form, they migrate in the, in the unit circle or root locus, where they become in the unstable region when the delay is increased. Basically, it creates the equivalent of negative damping. When it goes totally negative, it offsets inherent damping, you get instability. So it's a little bit strange.
Yeah, I think your point is correct. If the measured force is proportional to the displacement, you are right. If it is proportional to acceleration, such as the inertial force, it is a second derivative of displacement, so we have a negative sign in it. If you flip with the negative sign this graph, it becomes negative damping. So we are flipping back to here, then it becomes positive damping.
I mean, have you proven that point though using, let's say, control theory with stability in the transfer function approach?
Yeah, I think that's good comment. You can try it, but mathematically we can tell that it creates the positive damping.
But I think because of the assumption of a constant delay, which may not be really, the case, this may lead to that. I would suggest just to try to look at, some stability aspects using control theory to see if you can mathematically prove it. I understand your mathematics, I'm not being critical of that, but it just seems, counterintuitive. But it may be, as you say, because the force is not proportional to the acceleration associated with, that's the inertia force. That's going to be the inertia term. Okay, well, thank you very much.
Okay, thank you.
Thank you, Dr. Eccles. There is another question from Haitham. Haitham is my PhD student. Because we are doing something similar, Dr. Kwan, at the Wall of Wind between Lehigh and FIU. So Haitham is asking about the numerical model you're using or you used for the tall building model. Was it like a scaled model or like the complete full scale tall building? Like how many degrees of freedom, for example?
This is a single DOF system. The conventional aeroless test is done using the space pivoting model, just a single DOF system. So at this stage, we just want to replace the conventional aeroless test with hybrid simulation. We are considering to increasing the number of DOF in the numerical model side as well to accommodate TMDs or AMDs later on. But as a first step of development, we are using single DOF system.
That's great. Another question from Dr. Wang, Haifeng Wang, University at Buffalo. He's asking, does the wind speed affect the delay-induced damping? I guess that's related to Dr. Rickles' comment.
Wind speed itself, we didn't see influence or dependency of damping induced by wind speed. I think all this damping test was done without wind. So we carried out free vibration test and obtained this metrics or this table. And at the end, without having any wind, the measured damping was quite consistent with the damping equation that we derived. Once wind blows and how much wind induces the damping is really hard to measure, by the way. You cannot tell whether it's a wind-induced force or damping that influence the response of the bridge deck model.
I have one more questions. So when you do the real-time hybrid simulations, in your numerical integration scheme, does the wind force is pre-record wind force, or you measure it directly from your wind tunnel?
The wind force is directly measured from the wind tunnel, and we are feeding it in real time. So there's always one step delay. In this case, it is either 2 milliseconds for bridge deck section model or 5 milliseconds for the building test setup because of the device that we are using. But it is real-time wind force that is measured and that is fed back to the numerical integration scheme.
Oh, so on your experimental building model, you have some pressure taps on it, and then to measure it, convert it.
We are using wind-induced force with a loader cell.
Oh.
So from loader cell we can get wind-induced moment, and then that measured moment is fed back here. This term includes the inertial force of the specimen as well as the wind-induced force.
Thank you.
And Dr. Kwan, like just following up on that, so you use pressure tubes in this aeroelastic model, right?
No, we don't use pressure tube.
Oh, so it was only based on the load cell?
That's right. That's right.
Okay.
Yeah, one of the reasons is to make the experimental procedure simpler without using pressure tap. And another reason is that if you install pressure tap, the weight of the specimen increases substantially because of all the pressure taps and the tubes. And also the tubes inside of the model will vibrate as well. So this loader cell, we cannot use this loader cell, then we need to use the pressure tube. In that case now, in the practical application in real buildings, if the building geometry is not rectangular, then it's really hard to do integration and then measure or resolve force component only in this across wind direction. So that's why.
Yep, sounds great. Thank you. Is there any other question from the audience? Okay. Thank you again, Dr. Kwan. Thanks for your time. Okay, thank you everyone for the great discussion. We actually missed it's my bad, I forgot about the break that was supposed to be before this talk, but we can take it now, like 10 minutes break.